solutions about a singular point, just based on the definition of singular point and ordinary point from section 6.2, we'll use that. But here we'll classify a singular point as either being a regular singular point or an irregular singular point. Irregular singular point will be something that we definitely won't be able to use. But if it's a regular singular point, according to a theory by Frobenius, we can find at least one linearly independent solution. Typically, there'll be more than one, but he says at least one. So again, we examine a sub 2. We examine the nature of a sub 2 of x. We want to examine singular points, but in particularly to be able to determine if it's regular or irregular. Our solution will be around a regular singular point. So we're after how can we determine whether or not a singular point is regular. Well, here's what we'll do. If you take a sub 2 of x, you solve for 0, you get some value x naught. So if the factor x minus x naught appears at most to the first power in the denominator of p of x, remember that p of x is up here, right? So when I divide through by a sub 2, that's what they're saying. You're going to divide this differential equation by a sub 2, and you look at your denominators. So if x minus x naught appears at most to the first power in the denominator of p of x, and it appears at most to the second power in the denominator for q of x, and we say that x equal to x naught is a regular singular point. Otherwise, x equal to x naught is irregular. And why do they make the distinction? Is because if it's irregular singular point, then we make no notation in terms of a possible solution. Computers that we use to find such solutions would all break down. But we're able to get a solution about a regular singular point. So we want to investigate whether or not the singular point, if we can find such singular point, classified as either regular or irregular. So now understand when they use the terminology at most to the power, at most to the first power, or at most to the second power. At most to the first power means what? At most to the first power means what about the powers? It could be none or it could be one, right? So at most includes everything less than that up until that. At most 2 means could be none, 1, or 2, right? So basically you look at p of x, you look at q of x, you look at your denominator for p of x. If the power of a factor occurs at most 1, that means if it's none or to the first power, that's good. You look at that same factor in your denominator for q of x. If it occurs over in q of x in the denominator at most twice, that means it could be none, 1, or 2. It's going to be regular singular. Otherwise, it's irregular. Let's look at some examples of that. All right. Let's take this problem here. So what we're going to do is notice here that x to the third, if you set that equal to 0, this implies that x equal to 0 is a singular point. We need to classify, is this singular point, is it regular or irregular? So we're going to divide everything by x to the third. So we get y double prime plus 4 all over x times y prime plus 3 all over x to the third times y is equal to 0. Well, we know that x
x has the first power in P of x, right? But it has the third power in Q of x. So we conclude that here x equal to 0 is an irregular singular point. Okay. Let's look at another one. Okay, number 3. Just factor all of that down. Notice here that x equal to plus or minus 3 would be our singular points. Once you find the singular points, you know that all other points will be ordinary, right? Just the super inclusion of bifurcation, that if a set can only contain 2 types, then if you find one type, then everything else has to be of the other type. So here, all the other points are ordinary. It's the same thing for that previous one. So we come here and notice that this can be factored as x minus 3 to the second times x plus 3 to the second times y double prime plus x plus 3 times y prime plus 2y equal to 0. Now we divide everything by this a sub 2, so we get y double prime plus 1 all over x plus 3 times x minus 3 to the second, and this times y prime plus 2 all over x plus 3 to be squared times x minus 3 to be squared times y is equal to 0. So x plus 3 occurs, its power is at most once in P of x, and its power is at most 2 in Q of x. So that means that x, if the factor is x plus 3, then the 0 is x equal to negative 3, right? The term x equal to negative 3. Here, this guy is regular singular. Now, x minus 3, in P of x, it has power 2. Well, that's way above at most 1. So here, x equal to 3 is irregular singular. I think you get the idea there. Now, this quickly, you can look at this one. They have it factored for you already. So x to the first power is at most 1 in P of x, is at most 0 in Q of x. Excuse me. Thank you. So here, x equal to 0 is a regular singular point. X equal to 1, that's that factor of x minus 1, it occurs at most 0 in P of x, but here 3, not at most, it's 3. For Q of x was supposed to be at most 2, so that guy is above that. So here, x equal to 1 is irregular. I'll do one more here, and then we'll look at the problem. And this one is interesting because this one has imaginary roots, so how do you deal with that? Let's see. But you deal with about the same structure. You factor this. This is x times x squared plus 4 times y double prime minus 2x times y prime plus 6y equal to 0. Well, the singular points would be x equal to 0. You take x squared plus 4, set that equal to 0, you get x equal to negative 2i and x equal to positive 2i. So these are all singular points. Well, we want to know, are they regular or if they're irregular. So we divide everything by those factors there. This is x times x minus 2i times x plus 2i times y double prime minus 2x times y prime plus 6y equal to 0. So here we get y double prime minus 2 all over x minus 2i times x plus 2i times y prime. That x canceled out with x divided by x there. And then this is plus 1 all over x times x minus 2i times x plus 2i times y equal to 0. So x equal to 0 occurs non-zero in P of x and here once in Q of x. So this guy is regular. Excuse me. Don't want to be impersonal, but don't get too close to me today, right? Yeah. These days, we're kind of, really, okay, you stay over there. We'll talk on the telephone. Email. So x equal to 0 is regular, singular. What about x equal to 2i and x equal to negative 2i? Are they regular or irregular? They're all regular. Yep. It's too hot. Mercy. I think I burnt my mouth. Okay. So these are all regular. Well, why is that important? Let's see. Frobenius came up with an idea that if the point was regular, singular, then you can find solutions in the neighborhood here on some interval of convergence of 0 less than x minus x naught less than r. That's what we did that exactly in section 6.1. He said that if the point x equal to x naught is a regular singular point, then there exists
at least one solution. Now here, the solution is based on some type of index, R. You see, that's the summation as n goes from 0 to infinity times of c sub n times x minus x naught to the n plus r. Wow. The n plus r, or the plus r, is actually to restrain the interval of convergence to make sure that the solution actually exists about this this regular singular point. It refines the interval of convergence. It's very neat. And the theorem is, the proof of it is very categorical based on that. So here are my steps to this. Just take one and pass it around. Let me say one for myself too. My steps are listed there. I want to pass that out so you can actually see the hard copy as we work the problem, and I'll refer to the steps as I work the problem. So there are 8 steps here, a little bit more compared to what we did in the previous 2 sections. But the idea is there, the same ideal structure from how we work section 6.2 is evident here. So if I can't finish the problem, at least I can try to start it, and then I'll finish it on Wednesday. Okay. So we're going to try to work through these steps. Thank you, sir. Our first goal here would be to factor out x to the r from all summations, and then replace n with some factor k. We did that in the previous solutions about ordinary points. Evaluate each summation so that each summation starts at the same value. That's something that we did back in the previous section as well. This is new. Step 4, determine the values of R from step 3. R is called an index, and collectively we call those the indicial roots. Then step 5, we get to something common. So steps 5 and 6, something we've seen before, factor out x to the k and write the summations as one summation, determine a formula for c sub k. But then you want to make sure that the pattern for c sub k is based on each indicial root. So that'll be something new, and I'll show you that as well. Write the 2 solutions if possible with respect to the indicial roots. I remember in one year I gave a problem on the test, and the problem that I gave on the test, I typed it in wrong. I was trying to type in another problem where the solutions were very sweet, if I can say that. But when I mistyped, the solutions were not so pretty. And there were like 2 or 3 that was, they were able to actually solve it based on, I mean, it was still a differential equation that you could solve using power series, but it was very difficult based on my not copying the problem that I wanted correctly. And what happened was, on that particular problem, when you pick the indicial root, like one of them, it was interesting because everything in that particular solution came out to be 0. But for the other indicial root, you had a solution over there. And so what several people did was, when they got the 0 and it looked like you were actually dividing by 0, they said the whole answer was no solution. But it was actually a solution based on the other index of R. So, well, I won't have anything like that on the test. This is number 7. I'm sorry. Not number 7. Numbers 19 and 15. 19 is bigger, so I work that one. Okay. So here, x equal to 0 is a regular singular point.
And so if that's the case, x equal to 0, if that be the case, then we can use Frobenius. So he says to let y equal to the summation as n goes from 0 to infinity of c sub n here times, and this is x minus x naught to the n plus r, but here x naught is 0, so this is just x to the n plus r. Let's find, we need the first and second derivatives. So the first derivative is the summation as n goes from 0 to infinity of c sub n. Here this is n plus r to the x raised to the n plus r minus 1. And then the second derivative is the summation as n goes from 0 to infinity of c sub n times n plus r times n plus r minus 1 times x to the n plus r minus 2, n plus r. Now the problem is 3 times x times y double prime. We've got to break this down just to make it easier for us. This is 2 times y prime minus x times y prime minus y is equal to 0. Well, this is 3 times x times y double prime. That's the summation as n goes from 0 to infinity of c sub n times n plus r times n plus r minus 1 times x to the n plus r minus 2. Then this is plus 2 times y prime. That's the summation as n goes from 0 to infinity of c sub n. That's that first derivative. So we look up here. It's times n plus r times x to the n plus r minus 1. And then this is minus x times the first derivative. That's the summation as n goes from 0 to infinity of c sub n times n plus r times x to the n plus r minus 1, and then minus y, just the summation as n goes from 0 to infinity of c sub n times x to the n plus r, and that's all equal to 0. So step number 1, we're going to factor out x to the r from all summations. It is common everywhere. So step 1, we're going to factor out that x to the r. So it's going to be left times the brackets, 3x. And while we're doing that, let's just put that x inside that summation while we're there. So this is 3 times the summation as n goes from 0 to infinity, c sub n times n plus r times n plus r minus 1 times x to the n. We took out the r, we factored it out, and this is minus 2 times x to the first powers. This is just n minus 1. And this is plus 2 times the summation as n goes from 0 to infinity, c sub n times n plus r times x to the n minus 1. And you know, as you work on these problems, you kind of get the feeling that if computers had been created first, then we wouldn't have to go through all this, you know. So because we kind of
the learning back then was not with the computer in mind. And then so nowadays, computer science is so important. And so they didn't have computers back then, so they were left to list out all these summations, right? I don't know if you ever looked at, sometimes like in Wolfram Alpha, when you go and type in a problem and give the solution, some of their solutions come out to be power series, and you have to figure out, what's the solution that I'm looking for, not in the power series. I know with Maple, it loves to spit out a solution in power series, and you're not looking for that, so you have to go back and type in. There's a statement you could type in so that the solution is not in power series. You just get like a regular solution. But all solutions for differential equations can be written in power series. Just like how when you were introduced with Taylor expansion and Maclaurin expansion, you can take any function, if it's analytic, and you can write it as some type of power series. Right? Take e to the x, you can write that as the summation, x to the n divided by n factorial. So here, this is minus, I'm going to put that x on the inside, so this is the summation as n goes from 0 to infinity of c sub n times n plus r times x to the n minus 1. We took out the x to the r. Then that last one is minus the summation as n goes from 0 to infinity, c sub n times x to the n equal to 0. And my time is up, but let me just do one thing. I just want to solve for those indexes, those indicial roots r. I want to find out what they are, and then we'll save the rest for Wednesday, if that's okay. Is that okay? I kind of got our fingers sticky with this pork chops and turkey necks, and so I kind of wanted to stay there and kind of finish eating a little bit of it, So that was step number 1. We factored out that x to the r. Then it says replace n with k factor. Replace n with k factor. So that's something like we did before, where we replace those n's with a k factor. But here, unfortunately, if you evaluate n equal to 0, nothing cancels out because you got those r's there. So we can't say, I'm going to start this guy at n equal to 1 or whatever, because you got the r in there. So if n is equal to 0, you get, say, for example, c sub 0 times r minus 1. So nothing really cancels out. So here, what we do is, just like before, I'm going to let k equal to n minus 1. Here, let k equal to n minus 1. Here, k is equal to n minus 1. And then here, let k equal to n. So k plus 1 is equal to n. So we do that here, there, and here, and then over here let k equal to n. All right, let's do that and let's see what happens. So we get that x to the r is out in the front times the brackets 3 times the summation here. If we let k equal to n minus 1, then if n is equal to 0, k starts off at negative 1. To infinity, this is c sub n, and n is k plus 1 times here, n is k plus 1, so this is k plus r plus 1. Times x to the k plus 2 times the summation over here. K is equal to n minus 1. So if n is equal to 0, this guy also starts off, k goes from negative 1 to infinity of c sub
here, C sub n, but that's C sub k plus 1. This n plus r, where n is k plus 1, so this is k plus r. I left off a term over here. Let me go back there. This is plus 1 times x to the k. This n plus r minus 1, if n is equal to k plus 1, then that becomes k plus 1 plus r minus 1, which is just k plus r. So this is times ratchet. K plus r times x to the k, and that's a plus 2. Have to put that guy there. This k plus r to represent the n plus r minus 1, where n is equal to k plus 1. And then this is minus this summation as k goes from here. This is n minus 1, so if when n is equal to 0, k starts off at -1 to infinity. And this is c sub n. N is k plus 1 times, here this n plus r is k plus r plus 1 times x to the k minus the summation as k goes from, k is equal to n, so that k goes from 0 to infinity of c sub k times x to the k. Close that up, equal to 0. Okay. I'm getting hungry and tired, so I'm going to stop right here. Okay. And I just finished that on Wednesday. Woo! Let's just do that. That's 6.2, that problem over there, and then 6.3, this problem. They're a bit long. The reason why I was trying to get to the index R is that on the test, I take one problem and one part, so one question of A with this problem, 6.3, just tell me what are the indential roots. And then the next problem would be, what's the formula? And the next problem would be, can you solve this and just get the final solution? So I break the problem. Since the problem's so long, basically I give you just one problem for 6.3, which would consist of like maybe 3 or 4 problems on the test. All right, so the same problem just broken up into parts. Well, see you on Wednesday. Thank you.